So welcome to the third day of our course, and we are still with the second topic of reactive intermediates. In yesterday afternoon's session I talked about carbines, and in particular about N-heterocyclic carbines that have been used as catalysts. Today I want to talk, or this morning, first session, I want to talk about benzynes. And as you can see, I will look at the history of their discovery, the evidence for them existing and structure, and how they are modern methods for making them, and then some examples of how they have been used in synthesis. So the history here begins a long time ago when people found some unexpected results. So even going back into the 19th century, you would expect both of these sulfonic acid groups under these very harsh conditions to be replaced by hydroxy groups. But from the bisulfonic acid, the meta disubstituted phenol, resorcinol, was achieved. So at that time, of course, it was just a question to determine the structure. In fact, the structure was determined a little bit later than the first report. But no idea of how this had happened, because they didn't really have any ideas of mechanism in those days. But then you come forward to the 1940s, and Gilman, for example, these are not the only reports, but Gilman reported this reaction where he took a chloromethoxybenzene, treated it with a very strong base, lithium diethyl amide, low temperature, so in liquid ammonia, and instead of getting a direct substitution at the ortho position to the methoxy group, he got some meta product. And then a little bit later, in the early 1950s, J.D. Roberts, that's the Roberts of the old Roberts and Caserio textbook, did a similar reaction under similar conditions, and found, this time looked a little bit closer at the products and found a mixture of what looked like direct substitution and meta product. So clearly something unexpected or something unpredicted was going on here. Then, so this is Roberts, who was working at Caltech in California. Also contributing to this story was Professor Wittig, who of course received the Nobel Prize in 1979 for the Wittig reaction, but was also interested in benzynes, or at least these unusual reactions of benzene. And eventually the definitive studies came from Roberts in the middle of the 1950s with carbon-14 labeling of benzene, and also some other types of reactions. But this is one of the classic experiments where if you take benzene that carries, well, here's the starting material, chlorobenzene, that has been specially made to have a carbon-14 label. Of course, it's only a very small percentage of carbon-14 because this is the radioactive isotope, but nevertheless, carbon-14 only at the position where the chlorine is attached. Treat that with sodium amide, another very strong base, again in liquid ammonia, and found that there was a substitution reaction to produce aniline, but that the aniline was made up of two radioactive isomers, one where the carbon-14 remained at the position attached to the substituent, so the position attached to nitrogen, same as attached to chlorine, but there was also in a roughly 50-50 mixture, some aniline where the radio label was at an unsubstituted position. Now you would expect, if there really is benzene, this is what he proposed, that there was benzene, which would then have a carbon-14 at one of the two carbons involved in this supposed triple bond. You would expect a 50-50 mixture, because there would be no preference between the two. In fact, when you examine this much more closely, it's not exactly 50-50, it's actually a 47 to 53 ratio, and that's because of the very slightly different reactivities of carbon-14 versus carbon-12. But it's approximately 50-50, which tells you that a symmetrical intermediate must be being formed. And so there is the reaction we saw on the last slide with a mixture, but another important point was that there was no para substitution, so the reaction only affected the original chloro-substituted position and the next door position. If you block the next door position, so here is methoxy and a bromo this time, and a methyl group, same type of conditions, no reaction occurred. So you put all this together, and I've just picked a selection of examples here, but you put all that together and it suggests there is a symmetrical intermediate with involving the carbon where the original substituent was and the next door position, presumed to be some kind of elimination reaction of the hydrogen on the ortho position and the halide leaving group. That then is attacked by a nucleophile, in this case the same nucleophile as the strong base that's forming the benzene, and it can attack at either position. So this was taken in the 1950s to be good evidence for there being something like this. This is the way we conventionally draw benzene with a triple bond, but you could argue about what exactly the structure is. So this is a copy of the preliminary announcement by Roberts of the benzene intermediate. He says, no satisfactory explanation has been published for the rearrangements which often occur in the amination of non-activated aryl halides with alkali metal amides. So that was where people had just reported these unusual substitution products, but hadn't said about how they were happening. This is only the preliminary paper. The full paper came out 2 or 3 years later. So just to say again, the supposition is you start with a labeled carbon carrying a substituent, that there is an elimination reaction of HCl. The same nucleophile that was the base that did the elimination then adds back, but it can add at either end of this symmetrical intermediate. So what is the structure of benzene? You can draw a triple bond, but when you think about the molecular orbitals, it's very difficult to imagine a full additional bond in a benzene ring. In fact, much more recently, benzene has been isolated in solid argon at 8 degrees Kelvin, but it has a very short lifetime at room temperature. So you could argue whether that really means it's been isolated or not. But if you freeze it down to very low temperature, you can do some spectroscopic studies.